In this lecture, we're going to be looking at the analysis of slope failure, and we'll start by reviewing the concept of factor safety. Factor safety is a defined variable, and we can use multiple definitions for factor safety, but all definitions have to include the following features. Critical conditions, that is, marginal stability, have to correspond with a factor safety of 1. Stable conditions have to correspond to a factor safety greater than 1, and unstable conditions would have a factor safety less than 1. The factor safety analysis may be somewhat outdated in some areas of engineering, but it is still in standard use in a number of areas, including slope stability. Because most people use factor safety in the analysis of slopes, it remains the standard of practice in this particular area of application. When we're looking at the analysis of sliding on one plane, one of the things that we need to look at is, in order to complete our analysis, we need to look at all the forces acting on this potentially unstable block of rock or soil. And of course, the first force acting on the block is the weight of the block. So gravity is a body force acting on the block, and it has a magnitude of equal to the weight, and of course its direction is directly down. There's another way that we can look at the weight, and that is we can resolve it into components. If we resolve it into components consisting of a component that is parallel to the base of the slide and another component that's perpendicular to the base of the slide, we actually have the most useful components, or most useful way to look at that weight. So once we have it resolved into its components, we can remove the weight itself and just look at the two different components. This actually suggests that we should be looking at this problem in a coordinate system that is both either perpendicular or parallel to the base of the slide, and that is how we're going to look at the potential instability here. But we need to look at all the other forces acting on the potentially sliding block of rock or soil. Another component would be the reaction force that is placed on the base from the rock beneath the potential slide. Because if we summed forces in the direction perpendicular to the sliding surface, those two forces must be equal. So we also know the magnitude of the perpendicular reaction on the base of the slide, and that's equal to the W perpendicular. Those two have to be equal for us to have static conditions. Because we know that normal force on the base of the slide, we can also identify the magnitude of the frictional force acting on that surface, and that would be weight perpendicular times tan phi. This is something that you would have learned in physics, where we have the frictional force that's resisting the potential slide. And if we happen to have a material that has cohesion, then we would need to know the length of the base of the slide, and we'll call that length L, and we can take the cohesion multiplied by L, and we get the cohesive force for that may be helping to resist failure. To complete our analysis, we're going to look at all the forces that are acting parallel to the base of the slide, and we have W parallel acting in a direction that would promote sliding, and we have two forces that are resisting sliding, that is weight perpendicular times tan phi and C times L. To define factor safety, we will have the forces that are parallel to the base of the slide that are resisting movement divided by the sum of the forces that are parallel to the base of the slide that are driving this potential failure. That is, factor safety under dry conditions will be equal to the sum of all the possible cohesive forces times the lengths over which that cohesion is present, plus W perpendicular times tan phi divided by weight parallel. Why I have the sum here is because when we get to more complicated analyses, we don't simply have a single block, but we consider all possible layers. But basically, you can ignore the summation for the very simple application that I introduced in the previous slide. So, if we have time at the end of the semester, I'll come back to this particular issue. There are other kinds of slides that don't involve sliding on a plane. This is a rotational type failure, so we need an appropriate rotational based stability analysis. And for that, we look at a number of methods that originated with the Swedish circle method. The Swedish circle method is over 100 years old, and a number of assumptions that are in it we can't normally make, but it's still sometimes useful to use the Swedish circle method, and I'll show you a modern example in a few minutes. The assumptions of the method are that we have a uniform geometry perpendicular to the plane of the slide, that we have a circular slip surface, that we have uniform soil conditions, where both the weight of the soil is constant with depth and the strength is constant with depth. And that's not usually the case, but sometimes it is close enough to being true that we can use the method. We also need to have strength parameters that involve either cohesion or SU, drained shear strength, and typically a phi value of 0 for undrained conditions. Now, there aren't many soils that would have an actual phi of 0, but when we are looking at short-term conditions where the soil hasn't had a chance to drain yet, there are situations where only cohesion would be resisting movement. And in those, we can use the Swedish circle method doesn't use the sum of forces. Instead, we're looking at the sum of moments and setting those equal to 0. And we'll take our moments about the center of rotation for the potential sliding mass. We need to look at all the forces acting on our soil, and we really only have two. We have the weight of the potential sliding mass and the cohesive resistance along the potential slip surface. And those are the forces that are shown here. But now we need to look at moments about the center of rotation. To do that, we need to know the moment arm. So we take W times A, and you'll remember how to calculate moments from physics. We take W times A, and that's the moment acting clockwise around the center of rotation. And that must then be equal to, at limiting conditions, the cohesive resistance times its moment arm, which is R, the radius of the circle in question. When those two are balanced, that is R times the cohesive resistance, when R times that cohesive resistance is equal to W times A, we have limiting conditions. But in order to come up with a factor of safety for this application, we define it using those two moments. To continue with this calculation, let me introduce a few more variables and concepts. First, we'll have the length of the failure surface. This is just a circular arc, and we'll call that length L. Recall that equilibrium depends on requiring the moments about the center of the failure surface, or the slip circle, to sum to 0. So we're summing the moments and setting them equal to 0. R is the radius of the circle associated with this particular or possible failure surface. The total force that is resisting slip for a cohesive soil would be the cohesive strength times that length of the failure surface, so C times L. And the moment arm, A, that's associated with the weight, is the distance, perpendicular distance from the circle center to that weight. And then at equilibrium, we would require that cohesion times length times the circle radius is equal to the weight of the potential sliding mass times its moment arm A. Using a factor safety approach, we would, by analogy, instead of the block case, the sliding out of single plane where we had the sum of stabilizing forces divided by the sum of destabilizing forces, we now have factor safety defined as the sum of stabilizing moments divided by the sum of destabilizing moments. So our factor of safety in the Swedish circle method is CLR over WA. While there are a number of methods that have replaced the Swedish circle method, they all owe something to the Swedish circle method, and that's why it's still worth introducing. But in fact, there are still some cases where we do use the Swedish circle method, and one of those is going to be shown next. One of those cases where one can use the Swedish circle method is shown next. There are a number of issues related to slope analysis with the Swedish circle method. It typically involves a large number of circles to be considered. The circle that happens to yield the lowest factor safety is called the critical failure surface. The slope stability is then described by that minimum factor safety, and we often associate the factor safety with the center of a circle, which allows us to draw contours of factor safety when we do multiple analyses, and we typically have to consider multiple types of circles, including toe circles, and slope circles, and deep circles, and circles tangent to the base of a weak layer, and circles tangent to the top of a strong layer. So we have a number of different families of circles that need to be considered typically, but in a perfectly uniform soil condition, it's actually doesn't involve quite as many different kinds of circles to be considered. But there are also special cases where you have an actual known slip surface for a case where an instability is occurring in the field. That's what I'm showing here, and this comes from an example from a senior design project for a case from northwestern Minnesota, and here you'll see a picture taken from the air of a rotating mass where the toe is emerging up in the center of a river, starting to dam up the river, and you'll also see the scarp of the slope back up behind the river, where you can see there was this rotating mass, and it was the subject of a past senior design project for geological engineers. Here's a closer view of the scarp, or the upper part of the slope. It wasn't a very steep slope, but here's the scarp showing the farthest back this rotational failure ever got. And this is a close-up view of the toe of the slide area where soil was emerging after rotation up in the center of the river, causing it to dam up and threatening structures both upstream and downstream. The senior design students in this case were able to use the Swedish circle method to estimate the soil strength because they knew the actual slip surface, so they could get the soil geometry, and the one unknown that they actually had was the strength of the soil, because they knew the factor safety. This was slowly rotating, that is, along the slip surface, so they knew that the factor safety was exactly equal to 1. And by using the Swedish circle method, they could estimate the strength of the soil and specify how to adjust the geometry of the slope so that a more stable soil configuration was achieved. We've come a long ways from having to rely only on the Swedish circle method. In fact, there are a number of limit equilibrium analysis methods available, and these are typically referred to as a family as slice methods. In these methods, the potential failure surface is, or potential failure mass, is divided into a number of vertical slices. Assumptions are needed regarding the forces acting between adjacent slices, and these slice methods allow layered or zoned ground conditions to be considered, and limit equilibrium methods are appropriate for both dry slopes and slopes with water. And water conditions can present particular difficulties, but wet conditions are often one of the conditions most likely to lead to slope instability, and so we need to be able to consider both wet and dry slopes. Next, I want to turn our attention to jointed rock masses and look at the types of failures that can occur in jointed rock masses. And I'd like to introduce these different types of potential failures for jointed rock in engineering geology, because we have a broader audience in engineering geology, but more commonly the analysis for these is considered in the course rock mechanics. But because engineering geologists and those with rock mechanics expertise are sometimes working together on this, it's worth all the broader audience knowing these different methods. So let's take a look at some of the different ways in which jointed rock can fail in a slope. Here are 11 different modes of failure that we're going to consider for rock slopes, from sliding on one plane, sliding on two planes, toppling, buckling, raveling rock falls, complex block failures, multiple block failures, rotational failures, which we considered for soils, are also possible for rock, and multiple failure modes, where part of a slope is failing by one mode and part of the slope is failing by a different mode. And there are actually more complex modes than these that have been observed in the field, but we'll probably consider some of the early modes here first. There are a number of cases that I wanted to show images of that constitute raveling, or conditions where marginally stable conditions occur, but there's a sliding mass moving down the slope at the inherent strength of the material. This is probably most commonly seen by most of you when you were first playing in a sandbox, and if you piled sand high, you eventually got to the point where a sheet of sand would move down the slope. That's what's actually happening here. This is raveling, and it can occur very commonly in soil slopes, but also in rock slopes. And here are some examples. Here's one view of raveling. Here's another view of raveling on a rock slope, and this was taken at the end of a winter season in Utah, where each year the State Highway Department had to clean up after these rather small raveling failures that occur predictably each winter season. They might seem small, but they can also pose significant danger to people driving along the roadway. So that's another view of a raveling failure. And here's still another view of a raveling failure, where debris is collected at the base of a slope and typically collects each season or each year as a result of the wet season. Next, we're going to look at a number of different modes where we have to consider two different kinds of issues. When we have discontinuities in a rock mass, we have to first examine the kinematic analysis of a failure mode. That is, we examine the question, can a block move, where we're looking only at geometric considerations after we understand something about the geometry of the discontinuities. After we've decided that a potential block can move, then we can examine whether the block will move. To do that, we'll need to know more about the discontinuity strengths and do a different kind of analysis. But kinematic analysis looks simply at the geometry of the block and asks the question, can that block move? Here's the depiction of the kinematic analysis for sliding on one plane. To have the potential for a failure, in this case, we have to have the condition met being the plane of sliding must daylight into the slope. And here we see the plane of sliding being represented by the dip vector, or the steepest vector on the potential sliding plane, and that dip vector must daylight into the slope, as you see here. And that's a fairly straightforward depiction, but if the dip vector was pointing the other way, we would know that the potential sliding mass would not be kinematically admissible if it was pointing to the right instead of to the left. It just could not move. Here's a view of what's left after rock has slid along a single plane. So you see a smooth surface along which rock has slid, and you see some of the debris collecting at the toe on the right. Here's another case where part of the slope has already previously failed, and this potential sliding mass here is what's left and has enough stability to still be standing in the slope, but it has the potential to slide as well, slipping along that plane surface that the adjacent rock slid along. The analysis for this can often be viewed in stereographic projection. Some of you have seen stereographic projection before, and some of you haven't, so I'm not going to go into this extensively in this course, but for those of you who have seen stereographic projection, we often have the depiction of the cut slope shown by the blue great circle here, and if our dip vector plots outside that cut slope, as is shown here, then we've met the kinematic conditions for the potential for sliding on that plane. When we consider two planes forming a wedge, then our kinematic analysis is a bit different. In that case, the line of intersection defined by those two planes must daylight in the slope. And here you see the line of intersection of two planes, plane 1 and 2, being depicted by a line of intersection I12, and here it is daylighting in the slope, and the conditions then are met for kinematic admissibility of sliding on two planes for this slope shown here. In stereographic projection, this doesn't look that different than sliding on one plane, but instead of looking at a dip vector for a plane, we're now looking at an intersection vector. It must daylight outside the cut slope. So this is an example of the kinematic admissibility of sliding on planes 1 and 2. If I1 and 2 plotted somewhere on the right portion or to the right of the cut slope, then it wouldn't be a kinematically admissible mode, because sliding on that plane, those two planes, would not be possible in that case. But in this case, with I12 plotting to the left or outside the cut slope, it is an admissible mode. This is an example of what's left after a wedge failure has occurred. So you see two distinct planes intersecting, and they defined a wedge that previously failed from this rock slope. Here's another case where we have two discontinuities that combine to form a wedge, and you see just a small amount of the sliding mass at the base of the slope. Most of it had already been hauled away. And here we see a collection of debris at the toe of a slope after a wedge failure, or sliding on two planes in this case. Next, we're going to look at some toppling cases. Toppling analysis is partly based on empirical observations. We recognize that slip must take place between the layers in the rock, and because slip's going to take place along those layers, the friction angle between those layers helps to define the kinematic possibility of slope instability. Toppling may be more likely to occur with closely spaced discontinuity sets, and when we're looking at discontinuities that might be involved in toppling, we know that the strike of the discontinuities must be reasonably parallel to the strike of the slope. The way that turns out in stereographic projection is what we'll look at next. We'll have discontinuities dipping into the slope face, as shown here. And here you see some fairly closely spaced discontinuities. Here's some examples from the field where discontinuities are dipping into the slope face, but a potential sliding mass is already forming and has the ability to move further down the slope. Here's another example where closely spaced discontinuities help to define potential topple. And there you'll see in the bottom right field notebook for scale to help you see how big this sliding mass is. Here's another case of toppling from a quarry in Wales. And in stereographic projection, we end up looking at the normal to the discontinuities, and we find in red a zone in which the normals must plot for toppling to occur. And if the n vectors plot inside that red window, then we have a potential topple. And if the n's plot outside that red window, we don't. To get into the analysis of toppling, I'd encourage you to take rock mechanics, or when you do take rock mechanics, we'll go through this analysis in detail. Buckling is the next mode that I want to introduce. For buckling to occur, we need to have a discontinuity set that's nearly parallel to the slope face, and the discontinuity set must be fairly closely spaced for buckling to be a potential mode. Buckling is not commonly identified in the field, and it presents unique challenges for analysis. It's possible to recognize the potential for buckling in advance and avoid conditions likely to lead to failure, but it's rare for us to be able to look at something after buckling took place and say, yes, that was buckling. So I don't have good pictures to show for buckling. There are a number of complex blocks that I want to take a look at next. These need to be considered in excavations of general shapes, so they don't necessarily have to be a uniform profile, and that will often introduce the potential for complex blocks. Another case would be a circular quarry, so that you're going to have different orientations to the cut slope, and that will introduce the potential for complex blocks. And they're considered in discontinuity combinations in general analysis, and I'll show you some pictures of those. But for modes 5, 6, 8, 9, and 10 from my previous list, we really don't have any systematic analysis. We just have the different ways of classifying them, but they tend to defy analysis. But let me show you some examples of complex block failures. Here's one where you see 3 different discontinuities sets in this rock slope that combine to create this sliding mass. There's the toe of the slope there that you show as the lush green. That's what's left after a U.S. highway was removed from the base of the slope, and it was decommissioned due to the number of deaths that occurred as a result of the slope failures that occurred along this roadway. And after rainy seasons, the blocks would be out on the roadway, causing a number of deaths over the years in traffic accidents. This is a multiple block failure, and to help you get scale for that, if you look on the left side along the roadway, you can see a road sign, so you can see that this is a very, very big multiple block system that forms something of a column that rests on a plane that dips slightly towards the roadway, and this is an example of a multiple block system that would require some complicated analysis. Here's a rock fall. Here we see in spring, and for scale you can see some traffic cones on the bottom left, but we had in spring a weakening at the base of this rock slope, and that introduced the potential for some of this material that's now been undermined to fall down and be unstable. A rock fall. Here's a rotational failure in a rock slope, and we most commonly see rotational failures in soil slopes, but many slopes involve both soil and rock, and a rotational failure of this type can occur, and that involves both soil and rock, or could involve only rock. Here's a rotational failure that involved only rock, and this was in a mine in Western Australia, and you can see some mine straps and benching for scale in this cut slope, and it didn't stay stable, and it disrupted the mining operations as we had a rotational failure. Move down to, here's the view of that same slope where you can see the unstable debris in a heap at the toe of the slide, and probably a better view of that rotational failure surface. Here's another. I'm not sure whether this is rock fall or a rotational failure. It's a very steep slope, so it's difficult to say which mode this is. I would probably call it rock fall. This is a case from Queensland, Australia, that I had an opportunity to get involved in the analysis of, where they were looking at coal seam, and after they extracted the coal seam, they were left with a relatively thin shale layer on top of sandstone. Well, when the wet season came along, they suddenly had their shale layer sliding into the mine, making it unstable. What happened is, as they removed the coal seam, what was left was a thin shale layer on top of sandstone, and water would build up in the sandstone behind the shale. That decreased the effective stress acting on the base of the shale layer, and eventually led to instability of that shale layer. I've got some pictures of it next, but they're very hard to view because they involve the trace of the coal seam that had been mostly removed at that point, and coal does not photograph at all well. So here's that, you can see the coal seam in the high wall of the mine. So there's the coal seam that they removed over most of the mined material in the foreground. But if we look at the wall to the right, which is called the low wall, if we look at that wall, we'll see the sliding mass. Here you can see the scarp or upper surface of the sliding mass, where there's the scarp, and this is all debris that's moving down the slope, and they've had to remove some of the material at the toe to try and keep mining operations going. But this is an unstable mass, and it became unstable as a result of water building up underneath this shale layer. Here's another view where you see the head scarp of the sliding mass and all of this material moving down into the slope, endangering the people and equipment and the mining operations. I'd like to briefly introduce the concept of slope monitoring, but I'm going to focus more on that next week. So I'm going to break off the lecture material at this point and ask you to tune in again next week when the lecture will focus on slope monitoring systems.